Have you ever just looked up at the night sky, really looked and wondered, how on earth do we know what those stars are made of? Well, today, we're basically becoming cosmic detectives. We're going to find out how scientists can look at a tiny speck of light from billions, even trillions of miles away and, well, read it like a book that tells the secrets of the entire universe.
Seriously, it sounds impossible, right? We can't go to a star, we definitely can't scoop up a sample, so how can we say with any confidence that it's made of hydrogen and helium, or that it's zooming away from us at some mind-boggling speed?
For most of human history, that's all we had. A faint little glimmer of light that's traveled across an unimaginable emptiness just to reach our eyes. But it turns out, that one little beam of light, it's a message, and it is jam-packed with secrets.
Now, to read that message, we first have to unscramble it. So our very first step is to take that single, simple-looking beam of starlight and just split it wide open.
You've definitely seen this happen with a prism, making a rainbow on the wall. Well, astronomers use something way more precise, called a diffraction grating. Think of it like a piece of glass with thousands of teeny-tiny grooves etched into it. When light passes through, it gets sorted out, color by color, into a beautiful full rainbow. Scientists call this a spectrum.
And this technique, this is our master key for decoding starlight. It's called spectroscopy. And believe me, it is the foundational tool for figuring out not just what the universe is made of, but how it all really works.
Okay, but here's where it gets really cool. When we look at the spectrum from our own sun, it's not a perfect smooth rainbow. No, it's sliced up by thousands of super thin dark lines. It's like a cosmic barcode, and it's totally unique to our star.
So what in the universe is making these lines? For a long time, nobody had a clue. It was a complete mystery. And cracking this code, well, it took a complete revolution in how we understood matter itself.
Right. What process is out there stamping this complex, unique pattern onto every single star's light? The answer, it turns out, isn't in the huge emptiness of space, but deep inside the tiniest thing you can imagine, the atom.
So to get the barcode, we had to first get the atom.
Our idea of what an atom looked like changed a lot in just a few decades. We went from Dalton's idea of simple little balls to Thomson's plum pudding model, and then to Rutherford's tiny solar system. But it was Niels Bohr in 1913 who came along and added the final, absolutely crucial piece of the puzzle that would unlock everything.
You see, Bohr figured out that electrons can't just be anywhere they want around a nucleus. They're stuck on specific energy levels, kind of like rungs on a ladder. And when an electron drops down to a lower rung, it has to release a very specific amount of energy. It does that by spitting out a single particle of light, a photon, of a very, very specific color.
And boom, that's the answer. Every single element, whether it's hydrogen or oxygen or iron, has its own unique electron ladder. So, as the light from a star's hot core shines out through its cooler atmosphere, the atoms in that atmosphere absorb the photons that have the exact right energy to bump their electrons up to a higher rung. This process literally pulls those specific colors out of the light, creating those dark lines. Each element leaves its own unmistakable spectral fingerprint, the cosmic barcode. It's a chemical inventory of the star.
So, once we figured out how to read these fingerprints, it was like we found the Rosetta Stone for the entire cosmos. We could finally start writing the biographies of the stars. And what a biography it is. Just by analyzing this barcode of light, we can tell what a star is made of, how hot it is, and even how it's moving through space, whether it's coming towards us or flying away. It's all just written right there in the light.
Let me show you a real-world example. This is the spectrum from a comet called Hyakutake. We have never been anywhere near this comet, but we know for a fact that it has molecules like cyanogen in it. Why? Because we can see their unmistakable fingerprints right there in its light. It's incredible.
And the star's overall color? That's basically a giant thermometer. You know how a piece of metal glows red, then yellow, and then white hot as it heats up? Stars do the same thing. The bluer a star looks, the hotter it is. This all comes down to a principle called Wien's law, which perfectly connects an object's temperature to the color it shines brightest in.
Okay, so what about motion? Well, that's the good old Doppler effect. It's exactly how an ambulance siren sounds higher-pitched when it's coming at you and lower-pitched as it drives away. The same thing happens with light waves. If a star is moving away from us, its entire barcode gets stretched out and shifted toward the red end of the spectrum. We call that redshift. And if it's moving closer, you guessed it, the light gets squished and it's blue shifted.
So
Knowing a star's chemical makeup, its temperature, its motion, that's all amazing stuff. But this technique didn't just tell us about individual stars. It completely, and I mean completely, changed how we see the entire universe.
Armed with this powerful new tool, astronomers started pointing their spectrographs at all the weirdest things they could find in the sky. And in doing that, they started to solve some of the deepest cosmic mysteries we had. Take this, for example. For a while, astronomers kept finding these weird spectral lines in the sun's corona and in faraway nebula that didn't match any element we knew on Earth. They actually thought they discovered brand new elements, and they even named them coronium and nebulium. But spectroscopy eventually proved them wrong. It was just good old iron and oxygen, but superheated to such extreme temperatures that we just couldn't replicate it here.
And then there were quasars. These things were even weirder. Their spectra were so bizarre, they were totally unrecognizable. Nobody knew what they were looking at. The whole puzzle was solved when someone had the brilliant idea that maybe they were seeing the normal fingerprints of hydrogen, but just massively, massively redshifted. And that meant quasars had to be incredibly far away, flying away from us at insane speeds. It revealed them for what they are, the super bright, chaotic cores of very young galaxies, all powered by monster black holes.
But maybe the craziest discovery of all came from looking at entire galaxies. By measuring the redshift of galaxies in giant clusters, an astronomer named Fritz Zwicky realized they were spinning way too fast. I mean, impossibly fast. The gravity from all the stars we could see wasn't nearly enough to hold them together. They should have just flown apart. He realized there had to be something else there, something massive, something totally invisible. And that was the first real evidence for what we now call dark matter.
And that stunning discovery, the idea that most of the stuff in our universe is completely invisible to us, it leads us to what is maybe the most profound and humbling conclusion in all of modern science.
You ready for this? All the stars, all the galaxies, the planets, you, me, everything that makes these beautiful spectral fingerprints that we can see and measure, all of it makes up a measly 4% of the universe. The vast, vast majority is that invisible dark matter we just talked about, and an even more mysterious thing called dark energy. So think about that. The very tool that allowed us to finally read the story of the cosmos also showed us that we've only read, like, the first page. It answered so many questions, but it uncovered a mystery so much deeper than we could have ever imagined. It really makes you wonder, what other secrets are still hiding out there in the light, just waiting for us to figure out how to read them?